I'm just writing this out in somewhat excruciating detail because I want you all to be sure that this works. So this is how you would usually argue that these kind of arguments work. Okay, so you say, suppose it doesn't work. Yeah.
Can we say that introducing a non-reachable point to the graph and say that when it is not marked, the subgraph is there?
Oh, are you saying that I'm only showing one thing, which is everything that is reachable is marked? I'm not showing the other thing, which is everything that's not reachable is not marked.
Yeah, kind of. It's the other way.
Yeah. So you're right. Technically, one should show that also. But for everything that we mark, yes, we actually found a path, right? So that's the proof for why we only mark the right ones as reachable. Okay, so you start with everything being not reachable except the. Anyway, so this is I just want to tell you that this. Alright, so this is just a formal proof. Okay, so let's now go into the running time. Okay, so a little bit more interesting. So what's the running time of this algorithm? So how would you go about bounding the running time?
Number of nodes.
Sorry?
The total number of vertices.
Okay, that's one guess. So total number of vertices. Why?
Because at worst case all the nodes are reachable, all the nodes in the graph are reachable from you, and we are running the search over all the nodes, at least one. Yeah, just one, like if you're marking this.
Yeah, so your observation is that search of U is, or search of V is called at most once for every V. It's called at most once for every V. Okay. So this is a good observation. So this says that the number of function calls that's happening is only n, right? So that's true. But how long does each function call take?
Number of degree of that.
So you do go through all the neighbors, right? So, and each search of V, each call search of V the degree of V. Okay. So this is what we have, and so the total time is sum of these quantities, okay, because sum of all the vertices for whom search was called of degrees only. Okay, so sum over all V reachable, let's say, degree of. And this is of course less than or equal to sum over all the vertices. Degree of V. And what is this? This is what we just saw. This is 2 times the number of edges. And so there is also always a constant here. So there is, it's not just degree of V. If degree of V is 0, also you do something, right? So there is like plus O of 1. Okay, so it's, so this is just to be formal, to avoid degeneracies where the graph has no edges. Okay, so in this case, it's not like you're not taking any time. You might take some time. Okay, so it's C plus. So this is that. So this is very easy. It's just a linear time algorithm. Okay. So I just wrote O of that. Yeah.
Why did we consider the second one? Because if we are visiting every point, then the second part, that processing the neighbors, is already covered in the first one.
Yeah, so you're right. I mean, number of, if it's as big as as n, then you essentially so you're saying you don't need this extra n term. Okay, yeah. So basically, I mean, you're right, it's basically the size of the component that matters, size of the reachable component, but it's easiest to bound it by O of n, because otherwise you'll have to say whatever the size of that component is. So that's the reason I wrote that. And the size of the component is always related to the number of edges, right? Because any connected component you have at least many edges. Okay. So in this case, yes, you could have skipped this, but it's just convenient to write it like that. So I just wanted you to be aware that there's always some overhead. Okay. So once you call search on a vertex, there is something that happens. Okay. So even if it has no edges. So that's why I have this O of 1. Okay, so any other questions? Okay, so this is a very simple linear time algorithm. So it's linear time because this is the amount of space it takes to write down all the edges in the vertex. Right? So that's why it's linear time. So okay. So this is good for finding who all are reachable from a particular vertex U. Okay. So that's good. Okay. So now, what if you want to, in some sense, also find the distance of a vertex to U? Okay. So you found who all can be reached from U. Right, so you found maybe that V is reachable from U, and maybe you found that some other guys are not reachable. Okay, so for a vertex that can be reached, suppose you are interested in how many hops it takes to reach V. Okay, so does it take to reach V from U? So this is another natural thing you might want to find, right? Because you're not just interested in whether you can be reached or not, but you want to know what the shortest path line is. So can you incorporate? So how would you modify this search? Yeah, so that's one way of doing this, definitely. But okay, let's see why that doesn't work. So you could say, okay, so when you are doing search of U, you also add a candidate distance. Okay, and you could say, okay, initially I will call this with U and 0. And this will go through its neighbors. This will go to its neighbors. And let's say these neighbors are labeled 1, 2, 3. And then you will, when you recurse, you recurse with 1. And then you'll say search of 1 with distance equal to 1. So it's a equal to 1. So then you'll have these things. So you have 4, 5. These are the nodes. And then you'll say search of 4 with d equals 2 and stuff like that. Okay. So this is one try. But I claim that this is a problem for the algorithm that we just saw. So why is that? So in the algorithm that we just saw, we were always just first recursing.
One vertex.
Yeah.
Would there be a problem if you are sending distance?
Yeah, exactly. So if you do it this way, the problem is that, so suppose I started off the search at u, right? So you start off search with u with 0. This will end up assigning a distance value to just these three vertices. Okay, so it will say this is a distance 1, this is a distance 2, this is a distance, sorry, this is a distance 1, this is a distance 1. Okay? So it will assign distance 1 to those guys. And then it will start exploring the tree starting at 1. Okay. And let's say it goes to 5, and then it says 5 has distance 2, 4 has distance 2. Then it will start exploring the tree starting at 5. Okay? So it will start looking at a neighbor. Now what if 3 had a neighbor, okay, which is this vertex 6, and 5 also had an edge to this 6. So then this process will end up thinking that distance of 6 is actually 3, because it will first start looking at 5. It would have done search of 5 with distance equals 2. In this process, it would have found that 6 is reachable from 5. It would label it distance 3. Okay. And then, when you actually come to its parent, you will not explore 6. Okay. So 6 ended up getting the wrong distance. Right? So its actual distance is 2 from you. So there are like 2 paths.
But aren't we doing the depth only after the first level? Because only in the first level we are actually doing the breadth, and after that, why are we going down rather than going up?
No, the way I defined it, you always mark your neighbors which haven't been marked. Okay? So in the first level, when you call it with u and 0, you will mark 1, 2 and 3.
Like, wouldn't it be something like after 1 we got 5 and 4,
Yes.
then we proceed to finally with 2. And then
So that's what we need to do, right?
Right.
So is this reasoning clear? That the mistake we are making is after we searched from 1, we started off searching with 5, and this is not what you should be doing. Okay, so we should be actually starting the search with 2. Okay. But how do we keep track of where we start the search every time? So the standard recursion that you are doing, it will just recurse and it will. So how does recursion work, right? So when you make this recursive call here, so this is search of u, it will hand over the control to search of v, right? And then until that function called search of v ends, you're not going to get the control back to this procedure. So that's the slightly, tricky thing that you have to be careful with. So is this issue clear? That when you do a recursive call, you let over the control to that v, and until that finishes, you can't come back. So what's the way around this?
You can add it to a queue.
Yeah, so you want some kind of an ordering, right? So what you want here is some kind of a first in, first out thing. So what we are saying is, you initially you have u, okay, and all the neighbors of u should be processed first, and things that you get while processing the first guy, while processing 1, have to come after 2 and 3. This naturally suggests having some kind of a queue where you push in stuff, okay, and you just do this recursive calls with the first element of the queue. Okay. So this is what is called breadth first search, and this is the reason you need this data structure queue. Okay. So for those of you who haven't seen this, queue is a data structure. It is what you would think it is, okay? Like people standing in line kind of a thing. So it's a data structure where you can push elements so these operations are called push and pop. Okay, so you can push and push new elements, and they are added to the end of the queue. Okay, so you can think of queue as as some kind of an endless thing where when you push a new element, it's added to the back of the queue. So it's like a store counter kind of thing, right? So you have a store counter over here, and initially it's an empty queue, and then when you add a person, he goes and stands at the back of the queue. When you pop a person, somebody goes out from here. Okay. So that's a queue data structure, and you can pop elements. So this is one of these standard data structures that probably all of you have seen and used. Okay, so now we decided that we should maintain a queue. Okay, so and whenever we see a new vertex to be processed, we just add it into the queue and keep doing things as long as the queue is not empty. Yeah.
So we sort of just, every time you mark a node as reachable, you would put it in the queue, and then
Yes, we
once
write
they're
down
all
that.
marked, then you recurse on.
Yep. Yeah. So actually, I should have maybe I should have extra slide. Okay, so let's see what the formal algorithm is. Okay, so we want to keep track of a global queue, right? Because so we said that this whole thing of doing recursion introduces this thing of you lose control. This procedure loses control. So you maintain a global queue. Okay, so maintain a queue. And initialize the queue to just this single vertex queue. Okay. And now what you do is, as long as the queue is non-empty, so while the queue is non-empty, so you do the following. Okay. So you let V be the top of the, V be the first element of the queue. And let's now process this first element. Okay. So we will pop this queue. Or maybe we'll do that at the end. Okay, so we'll start with the first element, and we have to process it. Okay, so what does it mean to process it? Okay, so imagine your queue started with this queue, right? So you want to process U first. And we said processing just means adding things that are immediate neighbors that haven't been reached individually. Okay. So you still have this reachability thing, and you just say add all unvisited neighbors of V to the queue. Okay. And then you pop V on. Okay, so pop. So you just remove V from this queue. So that's the guy. That's it. Yeah, that's what you will write when you are implementing. Yeah. So, okay, so this is our algorithm, and you can. I haven't written exactly how you maintain the distances, but it's clear for us. Okay, so whenever you add it to the queue, you also can find out what its distance is. Okay. So, okay. So this is called breadth first search. Okay, so the order in which you visit nodes is now very clear. So basically, what you'll do is you'll first add 1, 2, 3, and then you'll start processing 1. And in this process, you'll add 5 and 4, but you'll add it at the end of the queue. Okay. And this way, you'll next time when you look at the top element, it will be 2, and so on. So this is a very simple way of finding the shortest distance. any questions about breadth first search? So here again, the advice exercise is start with the tree, make sure everything works out. Okay, so start with a tree. So some basic tree and look at U, which is the start node, which is the root node. And just evaluate mentally what this thing is doing, okay, what this procedure is doing. And this will tell you the order in which you are looking at. Okay. So this is called breadth first search. And here you have, so what's the running time of this? Can you do the same analysis? Yeah, it's the exact same. Okay, so basically you will never add an element to the queue twice, and all you are doing is processing one element of the queue after another. So if you think about it, you'll see that you could have processed, and by processing I mean this step, for every vertex exactly once, and processing that vertex takes time proportional to the number of neighbors it has. And that is only overcome. So overall it's overcome. Okay, so this is another simple, yeah.
So does that mean if you have two vertices U and V, that finding if U can reach V and finding the shortest path from U to V is the same?
So for unweighted graphs, yes. So yeah. So for weighted graphs, this could take longer because there could actually be short paths that will, short in terms of number of hops,
Higher weight.
but higher weight paths that you will first find. And then maybe you will find long but all small weight paths. So we'll see that in a bit. So, see, before I think I got the order wrong, but let me first state the shortest path problem. Okay, so this is for weighted graphs. Okay, so this is the thing that we'll see in a bit. And here the problem is very similar to what we saw before, but you have edges have weights. Okay, so every edge has this WE. Every edge E has some weight W. So you could have, just to give an example, so you could have something like this. Okay, so this could be the graph. And the problem here is, so if you try to just do a breadth first search, then you start with this vertex, let's say. You want to find the shortest path between this and, for now let's start with this V. So just doing a natural breadth first search won't give you the right answer, because in the first step you will see this as being reachable with the length 10 path. So that's not the shortest path, right? Because there's a 2 plus 4 which is short. So that's what you want to find. Okay, so you want to find the path with smallest total weight. Smallest weight. Okay, so the sum of the weights of the edges should be as small as possible. And we'll see in a bit how you, maybe we'll end up seeing it next time, how you can do this fairly quickly. Okay, so it'll be a slight modification of breadth first search, okay, but it turns out you can still do this relatively quickly. Okay. So before that, I wanted to, so since this class is supposed to be more of an introduction, I want to talk about connected components both in directed and undirected graphs. Okay, so far we've only been looking at undirected graphs, right? Because we've been looking at graphs where edges are just, they have no directions on. Okay, so the directed graph going from U to V does not imply being able to go from V to U. Okay, so reachability is asymmetric. Okay. So first let's define connected components formally for undirected graphs. Okay, so we've done this implicitly before. So connected component is sets of set of vertices S is a connected component. For all pairs U and V in S, exists a path from U to. Okay, so note that for now I am defining this for undirected graphs. Okay. So having a path from U to V means that there's also a path from V to U. So that is figure small. And for all U in S and V outside S, there is no path. Okay, so this is just what we defined. It's the natural meaning. I'm just writing it down for me. Because these kind of definitions become non-trivial for directed graphs. Okay, so this is how we define connected components. So now, if you have a directed graph, okay, so let's say you had something like this. Okay. And maybe you also had this much. Okay. So a directed graph could have edges UV and VU because they mean different things. Now, so note that reachability is now an asymmetric thing. Okay. Because, so for instance, in this case, you can reach U to V but not V to U. So reachability is asymmetric. And the question is how you define connected components in directed graphs, right? Because earlier we said a connected component is one which, for every U and V, there is a path from U to V. And this implied that there was also a path from V to U. So, for directed graphs, what people consider is what are called strongly connected components. So here, you try to define the same way. So, let me write this as SCC. Set S subset of E is set to be you have again these two conditions. So the first condition is for all U V in S, U is reachable from V and vice versa. This is what is important. Okay, so you need to be able to reach U from V and vice versa. And this is again the maximal such set. Okay, so by this what I mean is for any U in S and V not in S, Okay? At least one of these things is false. Okay? So either U is not reachable, either U is not reachable from U, or V is not reachable. Okay. So in some sense you can't add anything else to S while keeping it strongly connected. So this is what is called a strongly connected component. And so every every directed graph, it turns out, can also be divided into strongly connected components. Okay, so just like any undirected graph can be divided into connected components, every directed graph also you can divide it into these strongly connected components. Okay, so let's see example of this. So if you take this simple directed graph, okay, so these two vertices are strongly connected. So this is how you go about finding. Okay, so you start with two vertices that are strongly connected, and try to see if you can add one more, right? So if you can't add any more, then it means that that by itself is a strongly connected component. Okay, so can you add X? No, right? So X you can't add because from V you can reach X, but there's no way of reaching the other way around. And you can't add U either, so that's also a problem. So in this case, the connected component, strongly connected components just turn out to be these guys separately. Okay, so U is in a strongly connected component by itself, and V is in a strongly connected. So these are the things here. And so in the homework you will see this nice exercise. I mean, it's actually a very simple exercise about how if you have a directed graph and you break it up into the strongly connected components, okay, and you take two components, then there are only edges going from here to here, not in one of the directions. Okay, so all the edges between these two parts have to go in only one direction. The reason for that is very easy actually, because if there are two edges, then you could add at least one more. You could make these components bigger. So this is just a simple exercise. So you can't have this. Okay. So this decomposition is often very useful. Okay, so that's why it's good to think about this. And so the canonical example of a strongly connected graph is a cycle, because the simplest, I guess, example, because you can reach every U from every V, and using the path in the other direction, you can reach VT. Okay, so this is a canonical example of a strongly connected group. Okay, so I don't think we'll have time to do shortest paths today, but it will be a simple modification of BFS.